Bien. Bienvenidos a la primera sesión del Seminario de Operaciones de este año. Tenemos el primer invitado ahora, son nuevos que acaba de llegar, José, Carrasco, que se llama. Bueno, él trabaja en el área de economía, hizo su doctorado en
Wisconsin.
Y se incorporó a la universidad a fines del año pasado. Entonces, gracias
en julio.
Había pedido que se hiciera este seminario ya y se puso primero en la fila para este, así que le agradezco también a él. Y va a presentar hoy día el artículo llamado Search at the Margin. Así que muchas gracias.
Bueno, muchas gracias. Gracias por invitarme. Como decía Rodrigo, efectivamente yo debía haber presentado el semestre pasado, pero por unforeseen reasons no pude presentar, así que presento ahora. Entiendo que podría llegar a alguien que entiende mejor inglés que español, o alguien en Viña podría entender mejor inglés que español, así que voy a tratar de hacerlo en inglés, va a ser un mix, ¿ok? O si prefieren, bueno, ahí voy a ver. Okay. So I'm going to start in English then. It's a good time to practice. All right, so what I want you to do throughout this presentation is that think any situation in which you have been trying to sell an asset, okay, as general as that. Maybe your preference change, okay, maybe you don't like anymore your large collection of stamps that you used to have and you want to sell it, or maybe the environment change in a way that now you need to sell that asset. Here are some examples of that. I'm sure you have more examples, but one of them is you're trying to sell a large parcel to cover medical expenses, or failed collateralized lending. This is a situation in which the lender finds himself in a situation with an asset that he doesn't really like, so he wants to sell it, okay? A firm selling seasonal inventory by the end of the season is another example, or even workers like entrepreneurs or lawyers hiring out their time partially, okay? And also tickets, airline tickets, soccer tickets, where people might find themselves in a situation where they hold a position in the asset and they want to sell it, okay? So in all these cases, the selling process takes time. And the question we pose is a very simple one, is this one. What do we understand about the seller's optimal behavior? So very simple, I want to sell an asset. So how should I sell it? That's the question. Okay? So that brings us, that brought us to the literature, in particular to the sequential search theory initiated by McCall in the 1970s, but the focus there is indivisible assets. So the seller might be selling a car or a house, just one asset, okay? But if you think about all the examples we gave, and I'm sure the example you also thought about, what do all of those examples have in common? Many things, but at least three. One is the fact that there might be someone else that values the good more than you do. In the case of a failed collateralized lending, if I'm the lender, I don't want to really have the asset. Instead, I want to sell it. Second, there are frictions. So in order to sell this asset, I need to search for buyers. And third, and most important, the asset position might be divisible. Okay, all the examples we thought about might be the case that you want to sell half of the asset, or 1/3, or is divisible in general. Okay, so the challenge here is to characterize the seller behavior in this context. Okay, what do we mean by that? Well, what is the optimal selling strategy? How does the behavior change as I unwind my position? So as I sell my position, how do I behave? And how does my behavior change as frictions change? Okay, what trade-offs arise? So it's a very general question. What do we understand about a seller that wants to sell an asset that might be divisible? Okay, so let me use this slide to tell you the main contributions of the paper, and then I'm going to jump to the model. Okay, so the way I see the paper has two main contributions. First, to the best of my knowledge, is the first paper to answer this question in a context with frictions, without a formal market, and second, with a divisible asset. Most of the literature in sequential search theory has focused on single units or indivisible. Okay, so we pose here a theory of search with multiple units, and that's what we call search at the margin. Okay, so when I say divisible, that might mean many things. So in particular, what we do in the paper, we divide the paper in two sections. The first is when the asset is divisible, but you can divide the asset into integers. So I hold one house, two houses, three houses. And another alternative, if you hold a large parcel, well, in that case, you might want to sell 1/3, 1/2, 80%, so it's perfectly divisible. Okay, so in the remaining part of the talk, what I'm going to do is first I'm going to explain the multiple indivisible holdings case, and then I'm going to show you how that model extends to perfectly divisible. Okay, and again, the focus is behavior. Oh, I guess another thing I should say is that the reason why we divide this into these two sections is because in order to prove things in the first case, we use induction logic, whereas in the second case, we use recursion methods and recursion and contraction methods. So the method of proof is different, and that is, I guess, a sufficient condition for us to split this into these two sections. So this is the model, okay? Time is discrete, goes from 1 to infinity, forever. The seller owns an integer number of units of the asset, so 1, 2, 3, and so on. He might derive some dividend. Those are the ghosts. He might derive some value just by holding the asset. So think about if he holds 2 houses and he can rent those houses, and he derived from renting them a dividend kappa. Okay, and of course there's discounting, beta between 0 and 1. All right. 3 sources of uncertainty. First, there's an arrival of risk-neutral buyers. So every period I might meet a buyer who wants to buy from me. I might not. Okay. Second, once I meet the buyer is going to offer me a price. I want to buy a house from you at 10. Okay. And second, he might want to buy several houses at a time. Okay, so these are the 3 sources of uncertainty. I might meet someone, and conditional on meeting someone, he wants to buy L units from me at a price P each. Okay?
So, for example, you have 100 houses.
Yeah.
That's one asset and 100 units, or 100 assets?
100 units of the asset. Yeah. Okay? The offer dimensions might be dependent on variables, so we don't impose any restriction on the distributions here. And well, the only thing I guess is finite means on the price and on the L's. And this alpha L is the chance of meeting a buyer wishing L units. Okay. So. Yeah.
What do you mean with arrival of risk-neutral buyers?
Yeah, so the fact that they are risk neutral means that they only care about the money, and they don't derive a utility. There's no utility functions for the buyers. Okay, so the buyer cares just about the money. Okay, they just care about how much they pay for the house. Okay, so that's the model. Okay. So what I'm going to do here is I'm going to give you an example. So suppose every buyer that arrives wants to buy just one house. Okay. And for simplicity, I'm just going to assume that the kappa is 0. So no renting here, okay? Just to shorten the notation. So suppose you're holding one unit, one house. This is the McCall example. The value of that house solves that equation, okay? And I will explain why is that the case. The left side is the value of holding a house, okay? So how do I explain that value? Well, next period, I might meet someone, and that someone is going to offer me a price, P, for the house. And that price might be anything, right? It's a random variable. So I take the expectation of the max. If the price is too high, I might sell. Otherwise, I keep the house, right? So that's why we have the expectation of the max between P and V1. All right. So if you're the seller, what are you going to do? What is your selling strategy? When are you going to sell a house? Well, if you take a look at there, conditional meeting someone, the only thing I care about is the price exceeding V1. If the price exceeds the value of holding the house, I sell. Okay, and that's my reservation price.
So what was the beta?
Sorry?
The beta, what does it mean?
The beta is the discounting.
Discount.
Okay, so I'm standing today, and everything that can happen is tomorrow, right? So tomorrow I can meet someone, I might meet someone, and that someone might offer me a very good price, in which case I would sell, right? So my reservation price is the value of the house, right? And that's a positive number, so as long as the price exceeds R1, I sell. Yeah?
Yeah, it's similar to like an option price. Right?
Yeah, it's like an option, exactly. So search theory is all about optionality, and I'm going to be using that word a lot in the following slides. Okay? So suppose now you have two houses. How does this problem change? Well, my value is this. The value of holding two houses comes from the fact that tomorrow I might meet someone, and if I sell, I get the price, and then I keep my second house, right? If I don't sell, well, I just keep the value of holding two houses, right? So what is the reservation price? We solve this the same way we solved the previous one. Well, conditional meeting someone, I just care about the difference between V2 and V1, right? If this right side exceeds this left side, then I sell. Otherwise, I keep my two houses. So what is my reservation price? The difference of the values. Okay? So then the question, remember the question is, what about behavior? We want to understand behavior. So the question we might ask is, does the seller offer a discount? Does he charge a premium? What house is more expensive, the first one or the second one? Right? And to answer that question, we need to compare these two reservation prices. The reservation price to sell the first house and the reservation price to sell the second house. Right? And we do that. This here a little bit of math, but what I do here is I take this equation. I know that the reservation price is V2 minus V1, so I subtract V1 here, right? And you see that I can split this between beta and 1 minus beta. The beta enters here, so there's a minus V1 here. This V1 disappears, and I have a minus 1 minus beta V1. Okay? And the reason why I did that is because since V1 is positive, this whole term is less than just the first one, right? And that suffices to show that R2 is less than R1. Okay? Maybe I should write something here that the solution to the first equation, so V1 solves V equals beta expected max VP, right? Whereas V2 solves V equals beta expected max VP minus 1 minus beta V1. Okay? So you can think about this is the 45-degree line. Okay, I'm gonna do it here. This is V. This is the 45-degree line, and this equation here is an increasing and convex function, right? Something like this. So the solution is this. This is V1, right? And this one is a function that is always below this one, right? So it's something like this. So here is V2 minus V1, okay? So this is a fixed point reasoning. And I just wanted to explain to you so that you see what is next in the following slides, okay? So the behavior is that I charge a higher price for the first house. For the first house, that is a lower price for the first house, that is R2, and a higher price for the second house, and that is R1. Here, I'm going to write this, and maybe I should jump immediately to the equations. I'm going to use the word optionality here because this is just an option to sell the house. And here's the math, but I'm going to try to explain this just using this bullet, that the reservation price for the first house is just, it solves this equation, and the reservation price for the second one solves this one, okay? And you can see the difference between both. There's this omegas going on here, and this omegas, as Lorenzo was saying, this is just an optionality, right? So take a look at this equation. This is omega 2, is the option to sell at a price higher than R2. If the price is below R2, I don't sell. If the price exceeds R2, I sell. How much do I get? P. How much do I give up? My reservation price. So this is the optionality of the first unit. And this is the optionality of the second unit. Okay? So here, if you take a look at the reservation prices are just saying, well, if you sell today, you get the reservation price. If you don't sell, you're gonna get the reservation price tomorrow, right? Discounted, and you're gonna get an optionality also, because maybe the price exceeds that reservation price. But there's a discount here, a minus term that doesn't appear here, and the reason is because we explained that by a holding cost logic. When you have two units, since this is a sequential search problem, what you do is that you delay getting the surplus of the second house, right? You need to search, you need to sell one house first in order to sell the second one, right? So when you're holding two houses instead of one, you delay the surplus that you can get of the first house. You delay it, right? So that's a time cost, and that is the optionality of that house. So when you're selling this, you choose the reservation price, and the seller offers a discount, okay? Because once he sells the first house, he's going to be closer to get that surplus of the remaining house.
You mentioned that the buyers are risk neutral. It seems that the seller is also risk neutral, right?
Yes, the seller is also risk neutral. Yep. The seller only cares about the money. Okay, so the holding cost is going to be a discount. And we extend this to n units. Here. We extend this for n units, and we're able to write the reservation prices like this. Okay, this formula. You get the dividend today, and tomorrow what do you get? You're going to get the reservation price, the optionality of the nth unit, and you're going to offer a discount of the inframarginal units. Okay? Let me show you, this is simulations for general distributions, and this is what's going on. Okay, we just went through the two units case, but this is more generally. If you have 8 units, the value of holding assets, of holding this houses, are the white circles on the right panel. So of course, more houses are more valuable, right? But the value increases at the diminishing rate, right? And if you compute the reservation prices, The reservation price for the 8th house is very low. It's around 0.6. And as you sell, you charge a higher price for the remaining houses. For the last house you hold, your reservation price is close to 8. Okay? So you can think about this problem as a pricing problem. You want to sell, instead of houses now, 8 tickets, airplane tickets, say. And the question is, how do I choose the prices to sell those tickets? And the answer we give is that for the first seat, you should sell it at a very low price. And as your capacity is filled, you should increase the price. Okay? So that's the case when you have sellers arriving and wanting just one single unit. What if they arrive wanting several units? Well, if they want several units, many things can happen. Why? Because we need to specify what happens if the buyer wants more or less than the position of the seller. Suppose you hold 10 units. What if someone wants to buy 20? Right? Can you sell just 10? Or he just wants 20 and that's it? Okay? So suppose take it or leave it offers. Okay? The value of holding n houses is the sum, right? This is just an expectation, right? This is the sum over all alphas, right? But I need to split it into 2 parts. Why? Because if the demand is less than the position, well, I might sell the L units, in which case I get PL, my continuation value. Otherwise, I keep it. But if the demand exceeds my position, say I have 10 and the buyer wants 20, if he offers me a take it or leave it offer, I just can fill his demand. So I sell nothing and I keep my position. I keep my value. Right? So that's one thing that can happen. And let me tell you that in this case, reservation prices are not monotone. It's not the case that we have a nice figure, the one I showed you before, where the reservation prices increases as you sell your position. But, this is the good news, we recover that reservation price by adding an intensive margin optimization. So suppose every time I meet someone and he wants to buy from me 10, I can choose any number between 0 and 10. Right? So I can partially fill his demand. In that case, this is how the value function looks like. Here's some definition to avoid splitting this into 2 parts. But every time I meet a buyer, I can choose between selling nothing and selling the maximum amount he wants. Right? So this is an intensive margin problem. And in that case, we show in the paper that we recovered this monotonicity. And this is, I know it's ugly, but I'm going to say this, so just focus in these 2 panels. The black circles on the right panel, the black circles, are the value, the white circles are the value function, the value of holding n houses, n tickets, when buyers arrive and offer you a take it or leave it offer, right? So you see that the value initially increases at an increasing rate, and then it flattens. The white circles, right? Yeah.
When you mean that it's take it or leave it offer, it means that if he arrives and he says, I want 20 tickets, and I only have 10, I cannot sell them.
Yeah, it's 20 or nothing.
Okay.
All right? So if it is 20 or nothing, we're in the white circle world. And in that case, the value increases first at increasing rate, and around 5 units flattens, right? So if we compute the reservation prices, the reservation prices look like this, like the white circle. So they are not monotone, right? So initially they increase, then they go down, they go up again, and then they go down. All right? But if we change the problem, allowing the seller to partially meet the demand, we go from the white to the black circle. in which case the value function always increases, but at a decreasing rate. And what does it mean? It means in terms of the reservation prices, that the reservation prices are, again, monotone, right? That means that if you are an airplane, if you hold airplane tickets or tickets for Chile, Argentina next Tuesday, I guess, the question is, how do you sell it? Well, it depends on what the buyer's demand look like. If they just want to take, if they just offer you take it or leave it offers, well, it's a more complicated problem, because say that somebody offers you a price of 6 per unit, per ticket. Well, you might want to sell the 1, 2, 3, 4, the first 5 units, because the price exceeds the reservation price. But you don't want to sell the 6th, the 7th, the 8th, and the 9th, but you want to sell this one, right? So the problems, in order to solve the selling strategy, you need to account for global optimality. Should I sell the first 5 units, or should I sell 6, right? Or should I sell all of them, right? You need to account for that. Whereas if you can partially meet the demand, you just think at the margin. Should I sell the next unit, or should I keep it? Why? Because the reservation prices are monotone, right? And that explains the title of the paper, Search at the Margin. The seller thinks at the margin, and he only cares about the next unit. Okay?
One question.
Yeah.
Would the analysis complicate too much if we allow P to depend on N somehow? Because I was thinking of, for example, the airplane example, right? He needs to pay because it changes over time.
Yeah.
Classical revenue management models, right? You have the ones who pay are willing to pay less initially, and then the ones that are willing to pay more come later. Right?
Yeah.
Could we adapt that same to this?
Yeah, I think, I'm not sure, I haven't explored that question, but for sure, I think it's interesting, because as you said, you're right? I mean, in the real world, the price or my demand might depend on how much you have available, right? So yeah, for sure that complicates the model, but I'm not sure how that might change this.
No, not giving the dependence on what's available, right? Like in the case of the airlines, just because customers want to fly right earlier, right? Want to buy the ticket earlier, are willing to pay less. Like,
oh, you mean introducing time?
Yes. Somehow.
Oh yeah. So
absolutely,
yeah. So in the paper, we solve this for a general case with a distribution for waiting times. So every time you in every period, you face a distribution of waiting times, right? So you might meet someone with some probability, right? And as time goes on, that distribution might change, right? And yeah, we get the result that as you approach the deadline, you're more willing to sell, right? So the prices go down as you approach the deadline. Yeah. So here I'm just I'm presenting a simplified version of the paper, the model we have in the paper.
But P is always the same distribution, right?
P is a general distribution. We don't impose any restriction on P.
But it's fixed for all N.
Yeah. Okay. So this is, I guess, one of our main results is that search at the margin is optimal. And by that, we mean that you just need to care about, should I sell the next unit or should I keep it? You don't care about global optimality. And the reservation price is just the difference of the values. And the formula is this one. Okay. And you see that it has the same structure than in the 2 case that we just saw. That my reservation price is my dividend for that unit, and the fact that tomorrow I'm going to get that reservation price for sure, and as Lorenzo said, an optionality for that unit. But I offer a discount. There's a minus sign here, and this is a discount, and we call that a holding cost discount. Okay, and the discount, I'm giving the discount because if I sell that unit, I'm going to have to sell the N-1 unit, right? So I'm going to be closer to getting the surplus for each of the remaining units that I hold, and that's a discount. Okay, we approach this problem using induction reasoning, So we assume something and we verify that for the next iteration. And the reservation prices define a supply function. So this, if you flip the left panel, it's just a supply. The higher the price, I'm willing to sell more units, right? So that's the multiple indivisible holding case. I have 20 minutes, so I'm going to briefly explain how this model extends to perfectly divisible assets, okay? And then I'm going to show you a few figures, and then I guess I'm going to be done. So how does this model change compared to the previous model? Well, time is continuous. First, the asset position is no longer n, and doesn't take just integer values. It's any number between 0 and infinity. And there's an interest rate for discounting R. Okay, the same three sources of uncertainty. Here, I will present the plus on arrival case. So at this rate row, you meet a buyer, in which case he offers you a price, P, with a random purchase cap. This is equivalent to the demand size. So every time you meet someone, he offers to buy from you X at a price P. And again, offer dimensions, possible dependent random variables, and an assumption on the density that is bounded and continuous. Okay, so this is the way it works. I'm the seller at rate row, I meet buyers, and the buyer offers me a limit order. I'm willing to buy X units from you at a price P each, and I reply with a supply function. Okay, and then I continue searching with my remaining position. So the same way we did for the value here, we need to write an equation for the value of holding a position A. And that comes from this famous equation that a return is the dividend plus the capital gain. Okay, so what is the return on your value? Well, it's just the interest rate times the value, right? That's my return. What is my dividend? I get a dividend K per unit of asset. That's A times K. And what is the capital gain? The capital gain comes from the fact that I can sell this, right? So at rate row, I meet someone, and I'm going to maximize my profits, P times Y. My constraint is going to be that I need to sell something. I might sell 0, but Y cannot be a negative number. And the fact that I'm going to be constrained either by my position A or by the buyer's demand X. So whatever is the minimum, that's going to be my constraint. And I need to account for the fact that I have a continuation value. So when I'm selling this, I keep A minus Y, right? Why did I leave a space there? Because P and X are random variables. Okay, P and X. So I need to take expectation of them. Okay? And then you see that there's a VA on the right side, a VA on the left side. I can put them together and write a Bellman equation like this. So you see that it's multiplied by row. I bring it to the left side, and then I divide, and I get this Bellman equation. So this has the same structure than before. A dividend value first, and then a discount times an expected payoff. And that payoff comes from selling. Okay? And again, if we understand behavior here, same, I mean, in this multiple indivisible holdings, we needed to understand the reservation prices, right? So here, if we want to understand behavior, we need to understand the Y, my supply function. How much am I going to sell for at each price? And of course, you see that the Y depends on the V, right? Depending on the shape of V, I'm going to have a different Y. But at the same time, the V depends on the Y. So we have to do this simultaneously, okay? And everything starts by characterizing the value function, which is the V, okay? And I'm going to explain here, how do we do it here. For simplicity, suppose K equals 0, so no dividend. You see that the first term disappears. I just keep the second, right? Nothing else? And this is a contraction operator. You plug V function on the right side, and this, the output is a V function on the left side. Right? So this is a contraction operator, and so we use contraction methods to characterize what value function solves that equation. This is an equation, but instead of solving for an x or a y, we solve for a function, right? And the first lemma is that this is a contraction and has a unique fixed point, which means that there's a solution for that equation. A v function exists that solves that equation. Okay? What is a contraction? So, and that fixed point lives in this set of bounded and continuous functions. Okay? And this is an explanation of what a contraction is. If you take it basically means that if you take a function on the right side, right, and you compute the distance between these two functions, you're going to have a number, right? Now, once you apply the operator to those two values, to that function, once you apply the operator, you're going to have a different function, right? And if you compute the distance between those two new functions, it's going to be a smaller number. So you can keep doing this over and over again until you hit a fixed point. Whatever you plug on the right side, the difference is going to be 0. You plug something on the right side, you compute the difference is going to be 0, and whatever you get on the left side is exactly the same. So once you hit that point, you have solved for a fixed point. And the cool thing is that that fixed point lives in this set B of bounded and continuous functions. So what we do in the paper then is we characterize the smaller closed set in which this fixed point lives. Okay? Not only bounded and continuous, but we show several other things in the paper. Yeah.
How do you define the distance?
Is the supremum distance? Yeah. Okay, and we show, for instance, that this B prime set, that's mainly what we do in the paper. We characterize this set. We show that set is the set of strictly increasing and strictly concave functions. So it's not only the case that the fixed point lives in this big set of bounded and continuous functions, lives in the smaller set of bounded, continuous, strictly increasing, and strictly concave functions. Okay. Let me jump. I'm going to jump here. Okay. So the value function is strictly increasing and strictly concave. We use recursive methods. So that means that we can solve this problem, right? Once you meet someone, you want to maximize your payoff subject to that constraint over there. So we would like to use calculus and we would like to take derivatives here, but we haven't shown that the value function is differentiable. So that's another contribution of the paper. We provide a new proof for the differentiability of the value function. We show the marginal value exists. It's also bounded and continuous. And of course exceeds the present value of dividends. Okay, I want to hit the figures here. This is the equation that solves the marginal value function. And the only reason why I'm showing this is because it has exactly the same logic than this one. If you take a look at this one, this was the value for V2, remember? So you see that the first term that appears is the expectation of the max between V and P. It's exactly the same term there. So this is an equation for the marginal value. How much do you value as an extra unit of the asset? Well, I can sell it at any price that exceeds V prime, right? And there's a negative term over there, right? And the negative term here, we call that a holding cost, right? So there is exactly the same logic. You see, Lorenzo, that this is an optionality if the price exceeds V prime A minus X. So this is the optionality of all units between 0 and A, right? So that's the holding cost, is the optionality of all the remaining units that once you sell the marginal unit, you're going to be closer to selling all the remaining units that you hold. And for that reason, you offer a discount. Okay? And that discount, let me jump here. Let me jump here. That discount is this one, right? And we show in the paper that this discount is increasing in the position in A, but it's also concave. So once you write the value function, the marginal value function, like this, right? My reservation price, the optionality of the unit, omega, and eta, the discount. Since this is increasing in concave, with the minus, the marginal value becomes a convex function. Okay, and that's what we show in the paper. So the supply function looks like the right panel. Okay, so let me see if I have time to, I should explain this, yeah. So the left panel is the value function, right? If you hold 0, of course the value is 0. But the larger your position, the larger your value, of course, but increases at a decreasing rate, right? It's increasing in concave. Actually, strictly increasing in strictly concave function. In the limit, the value is just the present value of dividends, right? The slope, sorry, is the present value of dividends. Now, say that you meet someone that offers you, suppose your position is A0, and someone offers you to buy units at P0. How much should you sell? Well, at A0, you see that the slope of the value function is flatter, smaller than the P0, right? So that means that you value the margin unit less than P0. So you're going to be selling, right? At least the first unit. So you're going to be selling this, and where do you stop? Whenever the marginal value equals P0. Right? So you equate P to the value, to the marginal value, right? And this Y0 is your supply here. At price P0, I sell Y0. Okay? And the supply function is the blue function over there. So there's a minimum price to sell. If the price is too low, I won't sell at all. As the price increases, you sell more and more and more. And if the price hits V prime 0, so the slope at the origin here, right? You're going to sell all your position. So that's a sell all price. Okay? Simulations. The left panel is the value function. The middle panel is the marginal value function. And the right panel is the second derivative. Okay? So you see that as frictions increases, so you start in the green function, sorry, the yellow function, and as frictions increase, and frictions might increase by a higher discount or a lower meeting rate. So suppose it's harder to meet buyers, then your value goes down to the purple, then to the light blue, to the red, to the green, and to the blue. But not only the value falls, but also flattens, right? And this is the figure here. The marginal value falls from the yellow to the purple to the light blue and so on. Okay? Which means that as frictions increase, you're more willing to sell. Your reservation prices fall. Where might we use this? Where can we use this? This model, this is Williams 2013. That talks about airline tickets, and capacity. And you see that the figures, if you compare this figure, the left two panels with this one are very similar, right? I should have put them in a different order. This is the value as a function of the remaining capacity, the A, right? The value increases, but eventually flattens. It's increasing in concave. Right? The left panel are the reservation prices for airplane tickets as the capacity is filled. Right? So take a look at the blue one. As the capacity goes from 60 seats to 40, the price goes to say 50 to 150. Right? And the price for each seat increases as your capacity fills. And not only increases, but it's sort of has this convex function, convex shape, sorry, which is similar to our findings. Your value function is increasing concave, and your reservation prices are increasing and have this convex shape. Okay? And the second case where we think our model might fit is in this famous name your own price cases, like Priceline. Have you heard about Priceline? Priceline works in a way that you enter this website and you offer a price. You name the price you want to pay. I want to pay $100 for one night at in a hotel, right? And Priceline replies yes or no, right? So you might think that our model fits that structure because the seller, what he's doing is he's posting a whole pricing schedule like this one. So if someone enters Priceline.com and offers this price, it's going to be rejected. The price doesn't exceed the choke price, the minimum price to sell. If the price is something like C, right, and he wants to buy less than the amount, the remaining units, well, what Priceline might say is that, okay, I want to sell at that price, but not your demand. I'm going to sell less, right? In a case like B, Priceline totally fulfills the demand. Okay, I accept and done. And in a case like D, again, the price exceeds the sell all price, but the demand is partially filled. Okay, so we see our paper as a paper that talks to these cases where the seller posts not a price, but a whole trading schedule. Okay, and that's it. Let me use this last slide to conclude, and then if you have any question, we can keep talking about this. If there's one thing you should take out of this paper is that we extend binary search theory, where you either sell or you don't, single units, to search theory at the margin with multiple divisible asset position. The divisibility might be perfect divisibility or multiple indivisible holdings. Okay, the caps, the X, the demand size, is the driving force behind all our results. If suppose the demand are always infinity, right? Nothing really changes. So the concavity that we found in the paper is a result of this different demand sizes of the buyers. And we derive endogenously using either induction or contraction methods falling reservation price. The value function is going to be increasing in concave, and the marginal value is convex. The supply function is going to be an endogenous marginal cost that is driven by holding cost and applied to these cases of airline tickets and exploitation of resources. And future work, you might think this is a middleman that not only sells, but only can buy. Or you can fit this model into an equilibrium environment or asymmetric information. Or maybe when I meet a buyer, he doesn't know how many assets do I still have. So you can extend this model in many different ways. Hopefully others might take this and use it for their purposes. But the takeout message is that we extend search theory to multiple divisible assets, and we solve it, and we think about this as a pricing model that fits the airline industry and maybe others. Okay, so I have 2 minutes, so if you have questions, I'm more than happy.